Hi everyone, in this video we're going to discuss about the central limit theorem. So this is remarkably an important theorem in statistics, and it is mainly because the normal distribution has gained so much importance in statistical theory. So this central limit theorem talks about the normal distribution. So roughly speaking, this theorem states that the sum of a very large number of random variables is approximately normally distributed with mean equal to the sum of the means of the variables and the variance equal to the sum of variances of these variables. So it's like an approximation to the normal distribution. So we shall discuss about the theorem statement. Here we are going to discuss the Lindberg-Levy form of the central limit theorem, and we call the central limit theorem in short as CLT. The Lindberg-Levy central limit theorem is about the identically distributed random variables. The statement of the central limit theorem is as follows. If x1, x2, etc. xn are independently and identically distributed random variables with its expectation or with its mean as mu and the variance as sigma square for all I equal to 1 to etc. n, then the sum x1 plus x2 plus etc. xn is asymptotically normal with mean n mu and variance n sigma square. So this is what the Lindberg-Levy central limit theorem says. And this Lindberg-Levy central limit theorem is for the independent and identically distributed random variables. Since it is independent and identically distributed random variables, we know if it is identical, the mean expectation of x1 is also mu, expectation of x2 is also mu, and for all the xi's, this expectation value is mu. And similarly, the variance is also same for all the random variables x1, x2, etc. xn. So, for all these random variables, we get the expectation of xi as mu and the variance of xi as sigma square. And what this theorem, the central limit theorem says is that Sn, the sum of these random variables minus the sum of its mean divided by the root of the sum of its variance will follow asymptotically normal distribution or asymptotically standard normal distribution. So, Sn follows asymptotically normal distribution. Therefore, Zn follows asymptotically standard normal distribution as n tends to infinity. So, this is what the central limit theorem says. So if we note this statement, we can see that there are some assumptions in this central limit theorem. The first one is that the variables are independent. The variables are taken to be independent. Next, all the variables follows the same distribution. It can follow any distribution. It need not be like normal distribution, but it can follow any distribution. But for all those variables x1, x2, etc. xn, it has the same distribution. And also, the mean and variance exist for all these variables. For all the variables x1, x2, etc. xn, the mean and variance exist. Similarly, we can also see that all the variables has the same mean and same variance. So, these are the four assumptions that are there when we talk about the Lindberg-Levy central limit theorem. So moving on to the proof of the central limit theorem, we are beginning with the MGF of the random variables. We know what is the MGF of a random variable xi. So this is as follows. Mxi of t is equal to 1 plus t mu 1 dash plus t square by 2 factorial mu 2 dash etc. This is the general form of the moment generating function. Here the mu1 dash, mu2 dash etc. are the moments about 0 of this random variable xi. Since these variables are identically distributed, this expansion is same for all the xi's. So this expansion is same for x1, x2 and xn. Now let us consider the MGF of Zn, that is the MGF of Zn. So we can denote it by mZn of t, which is equal to m Sn minus n mu divided by root n sigma square of t, which I can also write as m Sn minus n mu divided by root 10 sigma. I can take the root of sigma square and take it outside. So it is t. So which can be written as m Sn minus n mu into t divided by root 10 sigma. Yes, root is only for the n. So we can use the property of the MGF where max of t is equal to mx of at, with which we have written this. Now we are going to use the property of the MGF once again, that is e raised to minus n mu and this function t by root n sigma into m Sn of t by root 10 sigma. So we know m ax plus b of t is equal to m is equal to e raised to bt into m ax of t, isn't it? Yes. So here also we can write Sn minus n mu as minus n mu t by root 10 sigma into mSn of t by root 10 sigma. Now we can expand this Sn as x1 plus x2 plus etc. xn. Why? Because Sn is the sum of these random variables. So this is equal to e raised to minus n mu t by root 10 sigma, yes, into m x1 plus x2 plus etc. plus xn of t by root 10 sigma. So this can be written as e raised to minus root 10 mu t by sigma. I can cancel this root n and this n, and what will be left is root n into product I equal to 1 to n m xi of t by root 10 sigma. Since xi's are independent, we know the xi's are independent and identically distributed, so we have used that property that xi's are independent here. So we can write e raised to minus root 10 mu t divided by sigma into, I am going to expand what this is, mxi of t by root 10 sigma. Mxi of t is 1 plus t mu 1 dash plus t square by 2 factorial mu 2 dash plus etc. So what is this? This is 1 plus t by root 10 sigma. Instead of t, we are going to write t by root 10 sigma mu 1 dash plus t square by 2 factorial into n sigma square, isn't it? Root is there. Instead of this root, there is n square. So n sigma square mu 2 dash plus this is going to increase, isn't it? The denominator term is going to increase. And what we are going to do is, here in central limit theorem, we are going to look for an approximation. And in the approximation means this n, the number n is going to be a large number. So since in the denominator we have n, the next terms, the sum of next terms will be like, it will be a small value which we denote by O of 1 by n raised to 3 by 2 whole power n. Why? Because we have this product and we know since this is independent, x1, x2, etc. are independent, we can write this as product I equal to 1 to n m of xi of this thing. And since this is identical for all this m of xi of t by root n by sigma, we can write it as this raised to n. That is why we have a raised to n here. And we are going to expand what is mxi of t by root n sigma, which is this thing expanded where instead of t we have t by root n sigma. So that is the only change. Since we have n in the denominator and as n tends to infinity, the rest terms will have n square and cube and it is increasing terms. As n tends to infinity, all these values will be near to 0. So we are going to write it as O of 1 by n raised to 3 by 2. Now what we are going to do is we are going to take the logarithm on both the sides. So logarithm on both the sides means log m zn of t is going to be taken. So what is that? There is a e raised to minus root n mu t divided by sigma. So logarithm of that will be minus root n mu t by sigma plus that term was like in bracket whole raised to n. So it will be n log of 1 plus t by root n sigma mu 1 dash plus t square divided by 2n sigma square mu 2 dash plus order of or O of 1 by n raised to 3 by 2. Isn't it? Yes. So this can be written as minus root n mu t divided by sigma plus n into we are going to expand this logarithm. So this is considered, this whole thing is considered as a function, suppose x. So the expansion of this logarithmic function is what we are going to do now. So that is equal to the n of 1 plus t by root n sigma mu 1 dash plus t square 2n sigma square mu 2 dash plus of 1 by n raised to 3 by 2. Okay. So I shall open here also minus the same term square, isn't it? Yes. So this is here. Now this is considered as log of 1 plus x. Log of 1 plus x. 1 is there and log of 1 plus x. The expansion of log of 1 plus x is what we are going to do here. So we have the term 1 here. Now what is left over is this term as considered as x. So t by root n sigma, the term is here. Now what we are going to do is we are going to consider the second term of this log expansion, that is t by root n sigma mu 1 dash plus t square 2 n sigma square mu 2 dash plus of 1 by n raised to 3 by 2 square divided by, this term is divided by 2. And it goes on. And it goes on. So this is the expansion. So which is equal to, we will get a much more simpler term because some of the terms cancel out here. So what we will get is t square 2 sigma square mu 2 dash minus t square 2 sigma square mu 1 dash the whole square plus O of 1 by n raised to 1 by 2, which is equal to t square by 2 sigma square mu 2 dash minus mu 1 dash the whole square. Sorry, it's not the whole square, it is just the square. I have taken these terms to be common, plus of 1 by n raised to 1 by 2, and that is equal to t square divided by 2 plus of 1 by n raised to 1 by 2. And why? Because mu 2 dash minus mu 1 dash, the mu 1 dash square is equal to sigma square. So the sigma square and sigma square cancel out. Why? Because mu 2 dash minus mu 1 dash the square is equal to sigma square. So sigma square and sigma square cancel out, and what is left would be t square by 2. And limit n tends to infinity, log m zn of t will be equal to limit n tends to infinity t square by 2 plus O of 1 by n raised to 1 by 2, which is equal to, this order term as n tends to infinity will be 0. So this is equal to t square by 2. That is m zn of t is equal to e raised to t square by 2. And we know e raised to t square by 2 is the MGF of the standard normal distribution. E raised to t square by 2 is the MGF of standard normal distribution. Therefore, Zn tends to normal 0, 1 as n tends to infinity. So it is just the expansion of log 1 plus x, which I mistakenly talked as log of x. No, it is log of 1 plus x. So it is just the expansions. So log of 1 plus x will be 1 plus x minus x square by 2 plus, and it goes on. So it's this alternative of plus and minus in the symbols. So what we have is, this term is taken to be this itself. N is there. Then log of 1 plus this term. So 1 is there plus this term minus this term the whole square divided by 2. And it goes on. So on solving these, we will get what will be left will be like a very few terms, and from that what will be left is t square term, because t square term is only term that will be left if we are to find. Other terms will go cancelled, because when opening the square, here we do have a square bracket, isn't it? This square bracket. So if we open this square bracket, other terms goes cancelled, and what will be left is this many things. So t square 2 sigma square mu 2 dash minus t square 2 sigma square mu 1 dash the whole square plus this order of term. Next, on taking this t square by 2 sigma square common, we will get this. This is sigma square, and what is left is, as n tends to infinity, it will be e raised to t square by 2, and which is the MGF of the standard normal distribution.